Okay, let's start. Good afternoon, everyone in Iran, and good evening, good morning, wherever you are. It's a great pleasure today to host Dr. Athena Akrami. Dr. Akrami started as a biomedical engineer and a control engineer from Polytechnic University. She graduated in 2005 and joined Alessandro Treves lab in CISA. She got her PhD in 2009 and joined Matthew Diamond lab, again at CISA, when she started her experimental work on rats, and she trained rats to do parametric working memory tasks. In 2012, she joined Carlos Brody's lab at Princeton to do her second postdoc at the Howard Hughes Medical Institute in postdoc. And she was with Carlos for 5-6 years, and I think in 2018, she started her own lab at Sainsbury Wellcome Trust Neuroscience Center in London. Her work coverages computational models, experiments, and theoretical works. And it's a great honor to host you today, and welcome back home, although virtually. Floor is yours.
Thank you so much. It's indeed an honor for me to be here talking to you, unfortunately virtual, but yeah, thank you so much for organizers for having me. So before I start the main talk, I would like to kind of present you with a small sample, a kind of a voice clip to hopefully make my point. I cannot see your faces, so I cannot kind of read your faces to see whether my trick works or not, but let's see. So please listen to this short sound clip. Okay, I hope you heard it, but I hope that you didn't understand it, and that's actually the point. You should not be able to understand it because it's a kind of a distorted voice. But now listen to this one.
The texture of experience is prior to everything else.
Okay, now. I hope it works. I hope that you all kind of got a smile in your faces, meaning that after you heard the normal voice, then went back to the distorted voice, you could understand it. You could disambiguate it, right? And this is basically, I was trying to make a point that as we navigate in the environment, we constantly deal with ambiguous and noisy situations. And what our brains evolved to basically kind of accumulate evidence, information, learn patterns in a completely implicit way, because we know down the line all this implicit knowledge will help us to kind of anchor ourselves into some familiar pattern and make sense of noisy, ambiguous situations. Okay, so the point is that, as I said, we gather this big part of knowledge about the environment in a kind of an unsupervised and implicit way. And in order to do that, our brains, not only our brains, all the species brain, they have evolved to be sensitive to regularities that are evolutionarily speaking relevant to us. Okay, and these regularities usually they unfold over time. Okay, right now that you're listening to me and are able to comprehend my speech, it's because in the back of your mind, even if you're unconscious about it, your working memory is working across different time scales in order for you to kind of stitch my speech together, right? And understand the words I'm saying, from which you can kind of decipher the sentence. From the sentences, you can decipher the whole paragraph and the whole meaning of what I'm talking about. Okay, so this is an example of a situation that the structure is unfolding over time, and your working memory is trying to stitch these kind of a temporally extended task for you. But you may also wonder how human babies in the first place, they learned human language, right? So auditory, the linguistic input for babies, it's pretty complex. It's a speech waveform, which is continuous, is non-segmented, but it's far from random. It's extremely structured, right? And at about month 7 or 8, babies start to pick up on these regularities and structure without anyone teaching them, right? So learning syntax is pretty much implicit and unsupervised, right? So they understand where are the phonemes, where are the word boundaries, and then they kind of understand the whole syntactic structure. So how does the brain learn complex bistructured regularities across time? This is the main question that in my lab we are trying to tackle. And in order to do that, I said that we somehow, all species need some sort of a faculty in their cognition, working memory. And here I'm using the word working memory in a very loose way, meaning that I refer to any internal representation of external world, okay, that then we have access to this internal representation, we can manipulate it, we can abstract things, we can just like discard information, and from which we can kind of learn regularities. And the interesting thing is that once we learn these regularities, they in turn can impact our working memory. Like, I can ask you to remember a set of words. I think you all agree that remembering gibberish is way more difficult than remembering a coherent sentence. Why is that? Because remembering coherent sentence taps into these learned regularities and kind of try to exploit that and use those coherence and correlation between words in order to remember them better, right? So there is this kind of a constant interaction between these two systems. And in the lab, we are trying to kind of have a systems neuroscience approach to understand the interaction between working memory and learning regularities. And the type of tasks that sit in this kind of a statistical learning are basically, some of them are very similar to the example of language that I told you, meaning that we have tasks for animals, mice and rats, that they basically are doing some cover-up task, and in the background, we expose them to some specific temporal patterns, and then we probe their brain indirectly by basically measuring their pupil diameter in order to understand whether they kind of learn these patterns even without us kind of rewarding them for finding those regularities. So, and some other paradigms and tasks are related to basically learning variables that have some sort of a probabilistic nature. And as an example, if someone grows up in London, for instance, or Tehran, they kind of form a prior belief about the distribution of the height of people in that society. Right? It had a certain mean with some uncertainty around it. But we can also update our priors. If now someone hops on a plane, go to another country, for instance, Indonesia, after observing a couple of examples of people walking in front of them, they can now update their prior, right? They kind of, they can update these prior distribution belief, right? How do they do that? How do we learn a distribution? How do we update that? So these are basically the type of kind of tasks that we are trying to understand in terms of statistical learning, when we always embed this task in paradigms that we call them parametric, for instance, like parametric working memory, that would allow us to disentangle different phases of basically from sensory coding and processes until decision making. This might sound a bit artificial because maybe in real life there is not a real distinction between sensory coding, memory, and decision making, but it will make our life as neuroscientists easier if we first have a paradigm that we can kind of deconfound these phases, and then hopefully later we can kind of study them in a more naturalistic and mixed way. So overall, in the lab, we try to basically kind of have pretty complicated cognitive tasks for human, rats, and mice, and we usually use high throughput training behavior, particularly for rats and mice in the lab, and human, we kind of use online platform, it's still high throughput, and we combine this behavior with various techniques to monitor and perturb neural activity in rodent brain, from imaging, electrophysiology, optogenetics, various techniques that are available. And we combine them always with some kind of a theoretical framework and modeling that can be either at the level of behavior, some normative model, or at the level of neural activity, some dynamical system, or some kind of a mechanistic model, in order to build a multi-level understanding of inference in temporally extended tasks. So this was a kind of a brief overview of what we are trying to do in the lab. Now, let me focus on a particular question, which is about this kind of learning, kind of a background in statistics and some properties of distribution in a certain sensory environment. Okay, so as I said, we try to study these type of behaviors in parametric paradigms. So when it comes to working memory, we used to have a really beautiful and powerful delayed comparison paradigm in monkeys. So it's a famous work by Ranulfo Romo and his colleagues that animals were receiving train of pulses on their fingertip. So it's a train of pulse with a certain frequency. So then there is a delay interval, and after that, a second pulse. And the animal is supposed to compare the frequency of the second stimulus with the memory of the first one. And you see that during the delay interval, they cannot still form any decision. So the neural correlate that we find is most likely just reflect the memory of the first stimulus, and it's not contaminated by the future decision or motor plan or things like that. Okay, so this paradigm didn't exist in rodents until Arash Vasehi and I, in the lab of Matthew Diamond, we pushed to develop it first in tactile domain for rats, and then when I joined Carlos Brody at Princeton, we developed it in auditory domain, and it's in terms of kind of a delayed comparison of, again, two sounds or two vibrations on the whisker of the animal. So there's a first stimulus, then there's a delay interval. It can be variable, as short as 100 milliseconds or as long as 20 seconds, and then the second stimulus. And after that, the animal should make a choice. So more specifically, let's look at the schematics of the task. So this is a top view of our task. There is an operant conditioning chamber. It has the wall, and so the front wall is basically kind of has 3 pokes. The animal pokes in the center, then receives the first sound. Okay, the first sound is a kind of a noise stimulus, meaning that at each moment in time, the amplitude of that sound comes from a Gaussian distribution. And then if we change that, the variance of that Gaussian distribution, we are basically modulating the amplitude or intensity of this sound. After that, there is a delay, again, variable, can be very short, can be very long. And after that, a second stimulus. And then there's a go cue, and only following go cue, the animal can withdraw and go to the left or right side of the box in order to kind of collect reward. And the way that we are delivering reward depends on the relationship between the two stimuli, meaning that if the second stimulus is louder than the first one, the correct action go to the left side of the box and go to the right the other way around if the first stimulus has a higher amplitude, okay? So we do have very similar paradigm in our human subjects, again, auditory and tactile. And now let's kind of try to focus and see what's happening in this behavior. So we are asking subjects, human and rats, to listen to a sound. So it appears, it has a certain amplitude. And then there is a delay interval. And after that, there is a second sound, okay? So we are asking a subject to compare this with the memory of the first. But what is the memory of the first sound? The thing is that memory is inherently noisy, okay? And depending on conditions, then the level of noise can change. Like, for instance, if you increase the delay interval, it becomes noisier. And so this little guy here that is supposed to compare the loudness of sound 2 with the memory of sound 1, you may just like completely forget sound 1. So in face of this noisy memory, our brains cheat in a kind of a smart way. What does that mean? That means that our brains try to remember the most typical sound. What is the most likely sound, right? And then if we kind of don't remember exactly what we heard, we kind of rely on that most likely one, right? Because most likely, if you just like remember that, it's on average, it's going to help us, right? To kind of maximize the reward or the gain in the task. So, and this kind of the typical sound, what is a typical sound, can kind of be estimated based on the recent history of the sound. If you kind of do some sort of an averaging for the recent history of the sound, we can form this kind of the prototypical sound, and then we can snap this noisy memory into that and kind of denoise it. Okay, so this is a phenomenon that has been first described by Hollingworth. He was an American psychologist in early 20th century. He did really beautiful psychophysics experiments. I really recommend you go back and check some of his experiments. He was also the one that saved Coca-Cola for Americans, basically, because the first time that Coca-Cola came out, it had a really high content of caffeine. So regulatory agencies were after it wanted to ban Coca-Cola, and Coca-Cola hired Hollingworth. And then he designed a set of really meticulous psychophysics experiments to measure various aspects of cognition. And then he showed that, hey, if anything, it's actually helping cognition. So his work from more than 100 years ago, they are really illuminating and interesting. And one of them is this describing this contraction bias, when basically perceived value of items that are held in working memory, it seems they kind of contract toward a prior that is formed by stimuli that are used in the task. So he was using a working memory task very similar to the delayed comparison of basically card sizes. So first card, then there is a delay, second card, and subjects were supposed to say whether the second card is just like shorter or longer. And he figured out that systematically all human subjects are overestimating the first card if it's too short, or underestimating it if it's too long. So it is contraction toward the mean is happening. And and since then, it's been replicated in various tasks, mostly in human, different modalities, and there has been a kind of a Bayesian view over it, right? So given the noisy nature of working memory, it's actually optimal to use some sort of a prior, and this basically likelihood of the memory that becomes fatter and fatter, noisier and noisier, we rely on that prior, which is the mean of the stimuli, and we kind of, in order to estimate it better. Okay, so let's see how it kind of manifests itself in our tasks. So again, first stimulus, second stimulus, we have this diagonal, which means that the first and second have the same amplitude, and the color codes the difficulty of the comparison. The closer to the diagonal, the more difficult the comparison. And here, this vertical line shows the mean of all stimuli, okay? So under contraction bias, if we have a pair of stimuli like this, the memory of the first stimulus moves toward the vertical line, mean, and by virtue of that, it's also getting closer to the diagonal. So the comparison becomes more difficult. But we can have pairs of stimuli like this that by virtue of going toward the vertical line, they go away from the diagonal. So the comparison becomes easier. So you can now immediately see that we can divide this stimulus space into different regions that we can call them bias minus, where basically kind of contraction bias is detrimental to behavior, and bias plus, where contraction bias is helpful for the behavior, right? So in the task, we are sampling this stimulus space like this, randomly interleaved. Also delay intervals are randomly interleaved. When we look at the mean performance of our animals, we see that the mean performance is pretty stable from 2 seconds and 12 seconds. At first glance, you might wonder, oh wow, these animals, first of all, have really good performance, 80%, and it seems that delay interval, we increase it, they just like remember it the same way, right? 12 seconds versus 2 seconds, they have a really good memory of the sound amplitudes. The thing is that it's misleading to look at the mean performance, because if we break down the performance based on individual pairs, so here, I'm just like putting the number on top of these squares, which shows the percent correct, okay? And you see that there is a certain pattern here, meaning that the performance from here to here gradually decreases, and from here to here gradually decreases, and there is this asymmetry of the performance here. I hope that you can actually just this kind of looking at these, compare it to these, you can see there is a similar pattern, right? Bias plus, bias minus, bias minus, bias plus. The same thing that we observe in our human subjects, okay? And the thing is that this pattern, this asymmetry, gets stronger as we increase the delay interval. And because some performance, there is this always bias plus and bias minus, if we just average them, the mean performance looks fixed and stable. But if you look at the pattern is becoming kind of stronger and stronger. Okay, so we can do a better job than just like eyeballing on the data and say that, oh yeah, this looks like a contraction bias. We can kind of fit the behavior with a simple regression model. So it's a model that tries to kind of capture the contribution of different components in the behavior. Okay, so because we as experimenters design the task with independent trials, so we expect the subject that fully learns the task to only basically have use the stimuli, sensory stimuli from the current trial and make a decision based on that, right? Whether SV is larger than SA or not. But the reality is that agents, they show suboptimal behavior somehow, right? So they do have various sorts of, they can have bias, they can have lapse, they can also have trial history, meaning that they, even if the trials are designed to be independent from each other, they still use the past, okay? So then we can, in this regression model, put sensory input from one trial back, two trial back. We can put some sort of another term that would capture the choice history or reward history of the animal. Usually it's in terms of lose switch, win stay. So win stay meaning that if I go to the left side, I get rewarded, I have a tendency of repeating the same action. But if I went to the left and I didn't get rewarded, I have a tendency to do the opposite action. Okay. And then another term which basically captures the contribution of overall mean, it's an exponential window over many trials, and we can kind of fit the tau of that exponential to see like how much subjects are basically integrating this long-term mean. And so the ideal performance, as I said, would just like have all these history terms zero. The weight of these regressors should be zero and only kind of rely on the current trial. Reality is that no, both rats and humans, they show significant values for these trial history regressors. So here this plot may sound complicated. The take-home message of that is that just like look at a rat and human subjects. So we are just like putting individual, the best fit values for individual subjects. This is for the sensory stimuli from the current trial, from the previous trial, and this captures this reward or action history. So you see that like humans and rats are pretty similar, right? And meaning that they do show these biases related to the sensory history. And the sensory history biases are actually stronger than this reward history, this win-stay, lose switch. And another interesting thing is that I mentioned we can kind of fit the best tau of that exponential window, and then that kind of tells us for how long these subjects are kind of estimating the mean. And looking at the rat population, it seems that some rats, there's a kind of a bimodal distribution. Some rats, they kind of integrate over tens of trials, and some of them are integrating over hundreds of trials, which is on its own very interesting and would be very cool to just try to kind of link that to other behaviors, right? An animal that inherently it seems it is integrating over longer time, what other behavioral phenotype it can show. Okay, so we had this task and the question was that what's happening in the brain? Okay, so to be honest, the thing is that now I'm narrating this story after, as if like I knew everything, right? All the results. The reality is that the way that it happened was very different, meaning that I had a working memory task for the first time, a beautiful working memory task in rodents, and I really wanted to study the neural mechanism underlying working memory maintenance, right? And then I started to kind of look into different candidate brain areas and inactivate them and see at how they are kind of impacting behavior. And I didn't know anything about contraction bias or anything about these nature, the noisy nature of working memory and how the behavior can be biased toward the past sensory stimuli, right? So this basically is after the story that I'm telling you kind of emerged after all pieces were put together. At the point that we were trying to figure out where to go to study neural mechanism of working memory maintenance, we didn't know much about rodent brain. From the monkey and human literature, we knew that prefrontal and posterior parietal cortices are involved in working memory. But whether they are also involved in parametric working memory of graded sensory inputs, we didn't know. And looking at other tasks in rats that they were tasks that relied on working memory, but they were not explicit working memory, like delayed orientation, accumulation of evidence, multisensory integration. The results from PPC inactivation, posterior parietal cortex inactivation, was very confusing, meaning that some tasks they saw impairment in behavior, some tasks no impairment, some tasks modality dependent impairment. Okay, so it was not really clear what we are going to see. In the next few slides, I'm going to show you some electrophysiology, optogenetics, and then modeling work to hopefully convince you why posterior parietal cortex is at least one of the substrates, neural substrates, that's some sort of a kind of an integration with this prior sensory knowledge and together with the working memory is happening. Okay, so we had animals that I was injecting them with halorhodopsin. So it's basically kind of a virus that it's an AAV virus that has halorhodopsin, and it's going to express this particular opsin in neurons. And then therefore, later on, when we shine light on these neurons that have this opsin expressed in them, we will be able to kind of shut down those neurons. So it's an inhibitory opsin, halorhodopsin. And I injected these animals on these specific coordinates. Okay, throughout the talk, I refer to this brain area as posterior parietal cortex PPC. The reality is that my claim only applies to the stereospecific coordinate. Why is that? Because posterior parietal cortex is a really large area in rat brain, similarly in other mammalian brains. And when we move from like posterior part to anterior, lateral to medial, a lot of things change. Connectivity with the rest of the brain changed dramatically. So I really don't know if I just like move 0.5 millimeter left or right, frontal or posterior, what will happen, okay? So the first set of results that we collected and I'm going to show you come from full trial inactivation. The animal pokes in, receives a sound, and the laser turns on immediately and remains on for the entire trial duration until the animal makes a decision, okay? So the results showed us that it seems if we compare the inactivation trials with control trials, when laser is off, the gray lines, they show control trials, we can suppress the bias plus and bias minus, right? So in control, we have significant and large values of bias plus and bias minus, and both of them goes to zero. And specifically, when we focus on these pairs of stimuli here, so these are psychometric pairs. They are called psychometric because basically we are changing the ratio between first stimulus and second stimulus, right? We are changing the distance to the diagonal. And so it has a kind of a psychometric is when we are varying one parameter of the sensory input systematically and then look at the behavior, right? So here we are basically changing the comparison difficulty and we want to measure the behavior, okay? So, and usually an optimal performance is a sigmoidal or a very sharp sigmoidal, okay? So focusing on that, we see that comparing control with laser on trials, we see that the laser on trials have sharper psychometric, right? And this was the first set of results that I ever collected when I was inactivating PPC. And you can imagine how confusing it was, because I was expecting either to see no impact on the behavior or some sort of impairment. And this was the first set of data, and I just like, psychometrics are getting sharper. How is that? That doesn't make sense. Like the behavior is improved. And that was the beginning of a kind of a detective story to figure out what's actually happening in this behavior. We cannot ignore this contraction bias and the use of the past sensory stimuli. And then looking at the rest of the stimulus set, we just like figure out, all the whole biases are going on. It's not just the improvement of the behavior. It depends where we are looking at. If you're looking at bias minuses, we think that the performance is improved. If you're looking inside the bias plus regions, we will think that the performance is impaired, okay? And then going back to that regression model, if we fit that and look at the weight of these regressors, we can see that only the sensory history regressors, now they have significantly smaller values. Everything else in the behavior, it seems, remain intact. Okay. Then what is happening in the neurons in this part of the brain? So here I'm showing you one example neuron. So y-axis is firing rate of this neuron, x-axis is time. The first stimulus happens 6 seconds later, second stimulus, then go cue, animal makes a choice, and intertrial interval starts. So you see that we are plotting here the firing rate in response to different values of SA. Okay, so as you can see, this neuron really doesn't care what is this sensory input during the first stimulus, delay interval, second stimulus. But then suddenly during the ITI, it starts to fire differently depending on what was the stimulus more than 10 seconds ago. Okay, so this is really interesting. It's some sort of a reactivation of this sensory input many seconds later. Okay, so when we kind of try to look at the summary of the neural activity across 5 different rats, we did a mutual information analysis. So mutual information analysis is when we have like 2 variables, X and Y, and we want to know that how much our uncertainty about Y decreases if we know something about X. Okay, so here X is the firing rate of neurons. We want to look at the firing rate of neuron and say that how much our uncertainty about some task parameter decreases. So that means that how much this X is kind of informative about Y. Okay, so here then I'm showing the mutual information between firing rate of single neurons, okay, and the sensory identity of either current trial in red or one trial back, trial I-1 in blue. Okay, so you see that there is a population of neurons that actually code the first stimulus during the stimulus presentation in PPC. But at the level of single neuron, it seems nothing of that remains in this delay interval. So it's cut because it's variable. And some small population also codes during the second stimulus, the identity of the first one, okay? And then nothing of that again remains until during ITI, it starts to kind of pick and come back. And when we focus on this blue curve, so blue is information about information that these neurons carry about the previous trial. So the current trial starts and there is this population here that are still firing in response to the previous trial. So you focus on that and we can look at the individual animals. So we have 5 different animals. We can look at the kind of how much their PPC carries this information about the past, and then how much they are also influenced behaviorally by that past. And if you look at the correlation, there is a kind of a really strong correlation between these 2 parameters, the neural information about the past and behavioral bias by that past, okay? So then we can kind of look at this correlation for different time windows, before the trial starts and after trial starts. And this is here in this magenta line here, and you see that this correlation peaks during the current trial, actually during the delay interval of current trial. So as if like somehow this integration of the working memory with this past happens during the working memory trial. And then I went back and I repeated the optogenetic experiments, but now focusing on different epochs of the task. First stimulus, delay interval, second stimulus. And you see that this kind of a sharpening of these psychometric pairs, psychometric curve happens only during the delay interval in activation. Kind of matching these results that somehow PPC is sending this sensory history to downstream area, wherever that working memory of the current stimulus is. It seems it's not in PPC really. And then it kind of integrates the two and impacts behavior. Okay, so I have a summary here before moving to the modeling part. Okay, so it seems that working memory is impacted by history of sensory events. And this is actually something optimal, given how noisy working memory can be, and given how in actual behavior, in daily life behavior, events are correlated. So we have this artificial task for animal that we designed every trial independent from the other trial, and we expect the animal to kind of function and understand these independence. The reality is that in daily life, events rarely happen in a completely random and independent manner. There is always some sort of a slow time scale correlation between events, and knowing this history would help us in a lot of the times to predict the future. Okay, so this some sort of a kind of a contraction bias that it seems is ubiquitous in rats, in human, is something optimal, and it seems posterior parietal cortex in rats causally represents this sensory history. Why causally? Because when we inactivate and remove and suppress this sensory history, the bias in the behavior is also reduced. Okay? So now the question is that, what is the mechanism? As I speculated, it seems that this working memory of the first stimulus is somehow is integrated by this sensory history somewhere downstream PPC. It's downstream because PPC inactivation didn't impair the working memory, right? It only kind of got rid of the sensory history. So it must be somewhere downstream. And this kind of integration happens during the delay interval. So to remind you again why we say that it happens during delay interval, first, the bias itself increases by increasing the delay interval. Okay, so here bias plus and bias minus for different delay intervals, and it seems that it kind of again matches that notion of noisy working memory, and the longer the delay interval, the noisier the working memory, and the kind of a higher reliance on this prior. And now in the lab that Elena and Victor, they are trying to kind of work on some kind of whether rats and humans and models, how they are sensitive to this background statistics in a sound categorization task that doesn't have working memory component. Okay, it's just basically categorizing one single sound. It seems that this sensory history bias is very different and is not there. Okay, so it seems that this kind of a disintegration somehow happens during the working memory. And again, as I said, it's very similar to this Bayesian notion of working memory recall, right? That it's noisy, we rely on prior to estimate that noisy working memory better. However, so in that Bayesian, we think that the animal somehow knows this overall statistics and this drift toward the mean happens. But the thing is that there is something else in the behavior that's very difficult to kind of reconcile with that notion. And what is that? It's the very short-term history biases, meaning that the bias toward the most immediate past trial. Okay, so here, look at the heat plots. For instance, this heat map here. So we are just plotting the action of the animal for different current trials. These are different pairs of SA and SB, but as a function of one trial back. So if there is no modulation but by the identity of one trial back, then this modulation across y-axis should be 0. But it's not the case. There is a very specific pattern here, okay? And we can quantify that pattern, and it exists in, again, different modalities and different species. And when we quantify that and look at this amount of bias, so we compare one trial back, two trial back, three trial back, and with the mean, and it seems that one trial back has really a stronger bias, right? So it seems that, so there is this aspect of the behavior that most of the behavior is actually biased by this most immediate short-term sensory history, okay? Then how can we reconcile that with this kind of a contraction bias? So I'm going to show you some work that Vijay did together with Claudia Klopath at Imperial. She's now, so she did it when she was at Imperial, but now she's part of our lab at SWC. And so she built a dual network model for working memory and contraction bias. So we know that this is a working memory of continuous variables, right? So a lot of the times the best model for a working memory of a graded input or continuous input, it's a line attractor. and or a kind of a line attractor is usually an estimate kind of it can be bump attractor, then we just like increase the number of bumps to infinity, basically, right? So we can sort neurons along an axis that basically kind of codes amplitude of A. And if there is a then certain input, it can activate a bump, and that bump will remain stable and represents the memory of that stimulus. So line attractor usually works based on a kind of excitation between neurons that are close by, and they are inhibiting far away neurons. So then they can create this bump of activity. Okay. So we have one line attractor for the working memory, and another line attractor for this PPC network or the sensory history network. And both are receiving this external input. The only difference between these two networks is that PPC has a slower integration time and has also firing rate adaptation. Okay, so now let's see what is happening in this network. So we have a stimulus 1, stimulus 2, the working memory network. It starts from somewhere random, right? Somewhere random there is a bump, then the first stimulus arrives. In response to that, the bump moves to that location. And if the memory is stable, the bump will hover around that throughout the delay interval. The second stimulus comes, moves toward that. And the way that we are reading out network is basically looking at the activity of this working memory network at these 2 time points. Okay. And then if the amplitude here is lower than that, it's one decision. It's higher, it's another decision. Okay. So now what happens under the assumption that working memory is actually volatile, right? So if the working memory is volatile, look at this example trial here that S2 is larger than S1. They are close to each other, but it's larger. So now working memory again starts from somewhere random. In response to the first one, moves toward that, stays. Now it's too volatile. It can't stay there throughout the whole trial and the interval, okay? It dissipates. And due to the input from PPC, moves to wherever PPC says to go. So it will be here, okay? So now you can see that this new location of the bump created a comparison that would give us kind of a wrong comparison. Now this S hat, the new location, has a larger value than S2. So this is similar to bias minus. But now we can have also trials that will give us bias plus, right? Because again, memory is noisy, it dissipates, moves to where PPC tends to go, and this new location is in the direction of the same comparison, but now kind of further away and better, right? So it creates bias plus. So overall, if you look at the behavior coming out of the model, we can predict everything that we got in our human and rat data. Meaning that, look at this plot here. You see this gradual decrease of performance from here to here, from here to here, similar to what we had in our subjects, and this kind of asymmetry around here and here, okay? But we also have this short-term, immediate short-term bias, meaning that if we look at this heat map, which is the history kind of performance matrix, that you see that there is a modulation across y-axis, what was the previous trial, and that's very similar to our human subjects, okay? So it seems that in this model, either the working memory bump survives, right, or it doesn't survive and jumps to where the history, sensory history input is, okay? So mathematically speaking, at a kind of abstract level, if you look at what is happening in this model, we have a pair of stimuli, S1 and S2 at trial T. So in a fraction of trials, this memory survives. It doesn't dissipate, and it will give us correct comparison. But in smaller fraction of trials, this memory dissipates. It's just like can't survive the noise and moves, okay? And now this new location of the bump, S hat, can either be in the same direction as the original bump and will give us still the correct comparison, or now it's actually in a wrong location and will give us error comparison, right? So this is basically what is happening in this model. The question is that what is this S hat? So S hat is a bump, right, that is basically driven from the distribution of bump location in PPC, right? Because as I said, if the memory is volatile and dissipates and cannot survive, it's go wherever PPC tells to go, right? So now the overall distribution, the marginal distribution of the bump on PPC is this pi, okay? And S hat is a sample from that pi. Now let's look, what is that pi, okay? So we said that we were kind of uniformly sampling these pairs of stimuli, right? They were all interleaved and with equal probability. If we translate that into the marginal distribution of stimuli, we get something like this, because there is some sort of an undersampling of these values around the edge. Okay, so all the pairs are sampled uniformly, but when we look at the value of a stimuli, these two values are undersampled. So the marginal distribution is something like this. The marginal distribution of bump location in PPC is also similar to this. It's only kind of a little bit narrower because of the slower time, slower integration time of PPC. Okay, so now again, if I want to kind of schematically show you what is happening in the network that is able to create similar contraction bias phenomenon on average, let's look at this kind of schematic. So we have these pairs, and here I'm just plotting pi. Pi is the distribution of bump location in PPC, right? So ideally, we want all these pairs below diagonal to stay below diagonal and give us the correct comparison. And these pairs above diagonal, we want them to stay above diagonal and give us the correct comparison, okay? But what is happening is that, look at this one. Look at this square here, the lowest value of SI below diagonal. So it's going to move and move wherever PPC is. PPC is somewhere here. So I think that you can appreciate that most of the places that this red square is going to move to is actually below diagonal, except for this tiny blue bit here. So it's most likely it's actually going to kind of give us a better comparison. As we move from here to here, this blue bit, which is on the wrong side of the diagonal, increases. So that would increase the chance of this square landing in a part of distribution which is wrong. Okay, so that would give us this the decrease of performance from here to here. Similarly for the blue pairs. So this blue pair again is going to move to somewhere on this distribution as we move down, this red bit of the distribution, which is the wrong part of distribution, increases. And that would give us this gradual change in the performance. Okay, so to be honest, I was not expecting it. This sounds very simple and trivial, and I was not expecting to see this at all, because I was really thinking that a very Bayesian computation happens, that the animal knows the distribution, knows the uncertainty, and kind of, depending on the uncertainty of working memory, kind of uses these prior distribution. But now this model just like opened my eyes that like, no, we actually don't need to do anything Bayesian. At the single trial, we can have a very kind of a non-Bayesian computation, let's say, but the overall performance looks Bayesian, right? So our continuous attractor model for PPC, which is again, it's very similar to the working memory network. It only has a slower integration. It can replicate all the behavioral results that we had. And this model suggests that short-term history bias, meaning that drift toward most recent past, right? Where is PPC right now, can produce the seemingly contraction towards the mean effect. And this contraction bias toward mean is basically an average effect over all the trials. Whereas if you focus on single trial, this volatile working memory jump towards the input from this PPC network, okay? And it doesn't drift toward the mean. Mean, it's not anything specific and special in this network. Mean is like any other values on the distribution. So this kind of brings us back to this kind of a probably a lot of you heard recently that like how can we talk precisely about Bayesian brain, that like the computations at the circuit level are Bayesian, which the hallmark of that basically is the access to uncertainty. And whereas some sort of a behavior that can be modeled using a Bayesian framework, right? And that Bayesian framework can kind of explain a lot of the things at the level of behavior, but at the level of computation, we don't know whether really kind of what is happening. So I think I'm going to stop here, just like briefly mention that we do have other tasks now in the lab, particularly Peter Vincent. He's a PhD student that is working with me, and Manish Sahani, and he's trying to kind of look at another aspect of working memory, which is kind of lost in paradigms like delayed comparison paradigm that would create only a binary response, right? So in the delayed comparison, we ask subjects to remember something and then compare that to something and only produce a binary choice, left or right, right? So we really don't have access to the nature of that memory. So Peter is now kind of is working on a memory reconstruction task that our human subjects, as well as he's working on rat and mice models to play with a joystick or a wheel to move basically a stimulus continuously and tell us where they think it kind of matches what they remember about the first stimulus. So these memory reconstruction tasks are very rich because they will be, then that recall, the memory recall, is not just like a binary choice. It has a lot of the information about that noisy memory. We hope that we can kind of, so it's the thing that like if we believe, again, going back to the kind of a Bayesian notion, that there is some sort of a posterior distribution in the brain that subjects think that they try to recall. Now that there's a posterior distribution, they need to turn it. They need to kind of collapse that posterior distribution into an action, right? They need to either create one value or kind of make a comparison task and create a binary choice. That collapse of the posterior distribution is very interesting and controversial. How we collapse the posterior distribution? Are we just like going with the maximum value of that posterior distribution? Are we going with the mean value of that? Are we randomly sampling from that distribution? So together with Peter and Vincent, we are trying to kind of look at these three scenarios, and so far it seems this paradigm can tell us a lot about these, and it seems it's not random sample, it's not the mode of the distribution, it's the mean of the distribution. But I'm going to kind of end the talk here because I would like you guys to ask questions, and I end here by thanking all the members of LIM Lab and thanking you all for listening to me. And I'm more than happy to get questions. Thank you.
Much for the great talk, as usual. We have 7 minutes here, and I encourage people to ask Dr. Akrami questions from her talk, and we have a panel session for half an hour after that, which moves to the panel room, and you can ask more general questions. So I'm opening them. Yeah, you can ask SNS guest number 5. You can ask your question. You can open your mic and ask your question.
Hi, thanks for the talk. In your model, there was a dissipation of the bomb, and in your model, can you hear me?
Yes, I do.
Yeah. And in your model, you showed it as a jump.
Yes.
And the input that is coming from PPC integrated in working memory is updated, and it's like a jump. Have you kind of investigated that how how is this jump happening, in the sense that is it a jump or is it a drift? And if it's a jump, is it happening early or late, or what is the timing?
So that's a great question. Yes, the model predicts a jump is basically because the PPC doesn't know where is the working memory bump, right? PPC is somewhere. PPC is kind of slowly integrating, and it's now the bump is somewhere. And this the bump in working memory dissipates, and then the jump means that once it dissipates, the network forgets about that and now responds to the input from PPC. So if you're looking at a working memory network, it appears as if like one bump disappears and a new bump appears, right? New bump is dictated by PPC. We know that you ask when it's happening in the model. The probability of these disappearance, reappearance, or the jump increases as we increase the delay interval. Okay, that's because the memory becomes that bump in the working memory network becomes more and more volatile, right? Whether that is the case in the brain, we really don't know. Okay, so now actually Vijay just started to kind of, so we don't have. The thing is that when did I start this whole project? I started working on developing the parametric working memory task in 2011 and 2011, and we are more than 10 years later, and I still really don't know where even in that brain is the working memory place. Okay, and so we don't have recording from that, but we do have a lot of recording from PPC, which is presumably this sensory network. And we do have some prediction based on this model how the activity should move in PPC network. So now Vijay is going to start to kind of dig into that and see whether we can kind of find some prediction of the model in the data, and hopefully we will have some based on downstream recordings from PPC, which are areas like PFC, PL or IL part of PFC. We might be able to kind of find the response during the working memory and see whether we can kind of really test this model, the jump really happens or not. Is that clear?
Thank you very much. By the way, very interesting work. Thank you.
Sure. Thank you.
Arif has a question. The question is, he wrote on the slide just before the first summary, how did you measure the psychometric functions between the two main stimuli?
Before the main summary. This one?
Arif, we can, yes.
How did I measure what again? Sorry, I missed that word.
Between the two main stimuli. I assume he's talking about the bottom part.
You mean this one, the correlation?
The correlation or the psychometric function?
Oh, the psychometric. So the psychometric is basically at the level of behavior, we change so we do have two sounds, right? So they have certain amplitude. So given the Weber law, if we want to keep the comparison of the sounds fixed, we are basically changing the ratio of stimuli. But then the thing is that we can kind of change them into the logarithmic scale, right? So then becomes the sound amplitude is basically dB, and then we can have fixed differences between the two sounds, and that will give us fixed comparison. If we want to create a psychometric, we would change that difference to just like smaller and smaller values, right? So imagine that the dB value, the endpoints of the psychometric, okay, you see that it's 8 dB difference between the first and second stimulus, right? That's a very easy comparison. In the middle is 0, right, when they are basically same. And then we are basically kind of putting 6 values in this range, and we are changing the distance between the two sounds. So this is how to create the psychometric. And then yellow and gray is just the psychometric coming from those trials that laser is off, so they are control trials, and yellow is for those trials that we were inactivating PPC. So optogenetics give us this possibility to have this kind of a temporally precise inactivation, meaning that we only are modulating brain activity when the laser is on. And depending on the preparation, the type of opsin and things, you can be sure that the effect is gone when the laser goes off, okay? And if you're asking about the correlation, it's basically, so we take a time window, and then we can, we do have an array of our animals, here 5 values, right? That they will kind of give us here I'm looking at the percentage of cells with significant mutual information. You can also look at the average mutual information in that population, okay? And then you will have a plot like this, a scatter plot, that the neural information, mutual information, is one axis, and then the behavioral bias of these individual animals, we do have that from the behavior, from fitting that regression model. We know that how much bias toward the previous trial they have. So we have that in another axis. And so from this scatter plot, this is basically kind of an R-square, looking at the R-square, and this magenta is plotting the R-square. I hope I responded to the answer, to the question.
Okay, thank you very much.